continue with Sn1 reactions and what are the characteristics of these kinds of reaction. So again, we have a halogen alkane. In this case, we are going to react with the water, which is the nucleophile in this reaction. In a certain solvent, we will get a substitution product, which is the alcohol with HBr as a byproduct. So bromide here is acting as a leaving group because it was attached to the electrophilic carbon. Now there are some players and factors you can relate to for Sn1 as well. Kinetics we know is first order. Steroid chemistry we have partial racemization. Substrate, it depends on the carbocation stability. Nucleophile has no effect on Sn1 reactions. The solvent will have an effect on the reaction, and this is about the solvation effect. Leaving group, the basicity of it. Now for the kinetics for Sn1, we know that the one here specifies the unimolecular reactions. Sn1, N here stands for nucleophilic, S stands for substitution. It is first order, and the rate of reaction depends only on the alkyl halide concentration, and it is independent of any kinds of nucleophiles concentration. So if you write down the rate equation, it is rate equals to K multiplied by the concentration of R, Br, not the books in the library. Now, so for this reaction rate, we can also define as the rate of disappearance of the alkyl halide. Okay, and small k, remember it is the rate constant. Back to your Arrhenius equations. Know this. Now the mechanism of Sn1 reaction. Not that difficult. Let's do this. Now it takes place via 3 steps with a carbocation as an intermediate. Rate determining steps in kinetics is defined as the slowest step of a multi-step chemical reaction. So for Sn1, we have a spontaneous dissociation of alkyl halide to give a carbocation. That means this bond here, CBr bond, will just break spontaneously, okay, and form a carbocation with a C+ charge. Now notice that these can also go back, because once you break this bond, you generate bromide, and bromide itself is a nucleophile. Minus charge, positive charge, they can attract and go back to the starting material. Not surprising. And this is exactly the reason why the first step here is the rate determining step. And this also accounts for the first order kinetics observed, because I need to wait for the carbocation to be generated first before my nucleophile can attack. If this is not formed, the nucleophile is going to sit there and wait. It can't do anything. As for the steroid chemistry, one enantiomer of the chiral reactant proceeds via the achiral carbocation intermediate. So the product mixture will be optically inactive. What it means is, after you form the carbocation, we know that right now around the carbon we are having a trigonoplanar geometry, flat, which means that it has equal probability of the nucleophile to attack from the suprafacial and anterofacial. Equal chances, about 50% each. So that's the reason why you would not favor a particular site. And hence, if the carbon is chiral, the whole molecule is racemic, which makes it optically inactive. Now, Sn1 reactions on enantiomerically pure substrates do not occur with complete racemization. What it means is, if my starting material is enantiomerically pure, that means only one of the chiral forms. So in this case, we have the R form. I put it under the reactions. You see that, hey, why I don't get 50% of each? Why? Because again, it's due to probability. So it doesn't mean whenever you have the formation of a carbocation, you must have 50% of each of them. This is not true. It is random by probability. Most of these reactions give a minor product in excess of inversion, partial racemization. This is a good evidence example of what I just talked about. Inversion means that backside kicking, attack from behind, backstabbing. Retention means it goes up from here, comes back in from the same side. Retention. For the substrate, if I form a more stable carbocation intermediate, the faster the rate of the Sn1 reaction. So we know that from our earlier slides, a tertiary carbocation is more stable than the secondary, in turn that's more stable than primary, than the methyl carbocation. Then your rate of reaction is fastest here. Now we introduce something called the allylic and benzylic carbocation. We know that when something has more resonance structure, the energy of the system is lowered. That means it's more stable. So in this case, if we have a formation of an allylic carbocation or the benzylic carbocation, the carbocation is stable as well. Notice this trend here for the relative reactivity. A tertiary carbocation undergo Sn1 reaction is 1,200,000 times faster than that of a primary carbocation. Look at that, tremendous increase. Wow! And the second comparison here, the carbocation stability, tertiary is the boss here, secondary is almost similar to benzylic, even though this is primary. Allylic, a bit weaker, but approximately the same, still primary, but due to its ability to form the resonance structure, it is stable, much more than an ordinary primary than a methyl. This is the worst. We can always fight this. Bad. Now next factor is the leaving group, the one that has left the substrate. We have a similar identical reactivity order found in Sn1 and for Sn2. So for a lousy nucleophile like water, it makes a perfect leaving group. Hydroxide, strong nucleophile, bad leaving group. As mentioned earlier on, if I want to convert the OH into Br, we can never allow it to undergo Sn1 reaction in this manner, because hydroxide will want to come back and attack R+. So what you're going to do is, you must hook on a tosylate, make it a good leaving group, and it will exit. For the nucleophile, we understand that the rate determining steps depends on the formation of the carbocation. So that kind of nucleophile does not interfere with the rate of reaction. It doesn't matter what kind of nucleophile, what concentration, the rate of reactions for Sn1 is going to proceed in the same manner. For the solvent, it is really interesting. Now any factor stabilizing the intermediate, which in this case is the carbocation, would increase the rate of Sn1 reaction. So now we know that the carbocation is a bit electron deficient because it's carrying a positive charge. If we have polar solvents such as water and methanol, what happens is the lone pair of electrons on the oxygen can form partial dative bond with the carbon plus charge and stabilize it. So it surrounds it and solvate my carbocation. Okay, so very good for the system, and hence it favor the formation of the carbocation. And non-polar solvents such as ether and chloroform are bad. Even though ether, you may think that for ether they may have an oxygen in the middle with a lone pair, but the thing is to surround the carbon. Imagine this is ether. Okay, I'll put the R here. This is big, electron cloud is huge. You experience repulsion with the carbocation, so no good. It can't even go in to donate the lone pair. But water is very tiny, H is very small, it can do its job well. Look at this, water 100,000 times the rate than ethanol, because I have a alkyl group here. So let's do some example. Predict whether each of the following reactions is likely to be Sn1 or Sn2. For the first case, first of all we check that this is a secondary alkyl halide, but it will form a benzylic carbocation which will favor Sn1. Good. Then now we check a solvent. The solvent is protic. Protic can stabilize the carbocation that's being formed. So, ding, Sn1. For the second case, this is a primary alkyl halide. DMF stands for dimethyl formamide. Right? Substrate is primary. The solvent is polar aprotic, and the nucleophile is Pretty alright, so it should be a Sn2 reaction. Remember, these are the players in this game. We check these and decide for the reaction, whether it's Sn1 or Sn2. Now recall that a nucleophile is also a base, right? Because both of them, in the definition, they have the lone pair of electrons. When the nucleophile or the Lewis base reacts with the alkyl halide, two kinds of reaction can occur. One is, of course, what we learned just now. It is a substitution. You attack the carbon that is electron deficient. Then you do a 1-for-1 exchange. Now the second kind of reaction that could happen here is the elimination reaction, where the nucleophile can pick up the neighboring hydrogen. Take note, it must be the one that's adjacent to the carbon that has a leaving group. So it's one of the next carbon, the H. The reason why it picks up this H is because with the polarization here, Br is delta negative, this carbon is delta positive, then the next carbon here must be delta negative, and the H here must be delta positive. Delta positive H means it has the ability to leave as a H+, which means that it is slightly acidic, very weakly acidic, and that's exactly the reason why a base can pick up this tiny H+. And then what do you get? You get the alkene, elimination product with two other byproducts. So if you begin with a 2-bromobutane with this kind of a solvent and your reagent, sodium ethoxide, recognize these ethoxides are fantastic bases. They like to cause elimination. Then you get alkene, 2 isomer, 2-bromo-2-methylbutane, alkene again. So for elimination, you get a mixture of alkene products. Now we try to follow what we call the Zizas rule. The one that's more substituted for the alkene, it will predominate, because again we try to form a more stable product. Reason: it is more stabilized through hyperconjugation via the alkyl groups.